Many people live and spend a great deal of time inside buildings, and many of them take it for granted that indoor environments are comfortable and their lives are safe. However, behind the comfort of indoor spaces lies a multitude of engineering designs. Today, I'd like to introduce each of those designs one by one at Hudson Yards. What do people need in order to live comfortably? There are many things, but among them, proper temperature and humidity, as well as clean air and water, are absolutely essential. To create such an environment indoors, ventilation and drainage are essential elements. The system developed to address this is HVAC. An HVAC system manages the airflow within a building and controls temperature and humidity to maintain a comfortable indoor environment. It comprehensively handles air circulation, heating, cooling, and filtration. The HVAC system on the Hudson Yard deck plays a crucial role in maintaining air quality and removing heat in the complex space built above the rail yard. This system controls indoor temperature and air quality through chillers, unit heaters, and air conditioning units, and works in conjunction with a forced ventilation system to support efficient air circulation. There is a park at ground level above the deck, which also poses a design challenge for the deck structure. That's because plant roots are vulnerable to high temperatures. To solve this, a subsurface cooling system was created. It circulates a cooling liquid through a sophisticated tubing network to block heat from the soil and help plants grow in an appropriate temperature environment. Since many people and trains pass through the deck area, a large amount of ventilation was required. Thus, the large-scale ventilation fans were used. These high-capacity fans are installed to promote air circulation in large spaces and are mainly used in large buildings and industrial sites. They effectively control airflow, remove smoke, heat, and harmful gases, and supply fresh air. The massive ventilation system installed on the deck uses 15 fans that circulate air at a speed of 45 miles per hour. These fans are based on technology used in commercial jet engines, efficiently expelling heat and exhausted gases generated by trains while supplying fresh air. As a result, it became possible to maintain a proper temperature and supply clean air within the deck area. Now, maintaining proper humidity is necessary, and to achieve that, a drainage system is essential. A waterproofing system on the deck had multiple layers, including waterproof concrete, polyurethane waterproof membranes, PVC sheets, and crystalline waterproofing agents, and it prevented flooding or leakage beneath the platform. First, waterproof concrete is a special type of concrete with excellent water resistance, containing chemical additives to prevent moisture penetration. Its main feature is that it blocks the pores within the concrete, preventing water from penetrating. The construction method involves mixing a special waterproofing agent into regular concrete. Then, the concrete is poured to activate its waterproofing performances. Next, the polyurethane waterproof membrane is a waterproofing material with rubber-like properties. It has excellent flexibility and provides effective waterproof performance in various environment conditions. The main features of this material are its strong resistance to moisture, excellent adhesion, and minimal deformation, allowing it to maintain stable waterproofing performance over a long period. The construction method involves applying polyurethane in liquid form and allowing it to dry, forming a highly elastic waterproof membrane. This method is well suited for specialized surface, sealing the pores on the surface to block moisture penetration. Third, the PVC waterproof sheet is a waterproofing material made from synthetic resin, known for its strong durability and excellent waterproof performance. It is unaffected by various climate changes and is easy to install. PVC sheets are especially efficient as they can be applied over the large areas. The installation method is also simple. The sheets are cut to the desired size and shape, and the joints are sealed using a special welding tool to maximize waterproof performances. Lastly, the crystalline waterproofing agent is added into the concrete, and when water penetrates, it triggers a chemical reaction that forms crystals within the concrete. These crystals block the water pathway, providing an effective waterproofing method. This method is permanent, requires no maintenance, and environmentally safe. The construction method involves either mixing the crystalline waterproofing agent into the waterproof concrete as an additive during pouring or applying it to the surface after the concrete has hardened. To proceed with construction, the four materials are applied in order. First, waterproof concrete is used as the base layer. On top of that, a polyurethane waterproof membrane and PVC sheet are added to form multiple layers of waterproof protection. Additionally, a crystalline waterproof agent is used to automatically seal any gaps if water does manage to penetrate. This multiple-layer waterproofing system blocks water infiltration between the railyard and the platform, ensuring that railroad operations are not disrupted. Despite those efforts, it was not able to completely resolve the drainage issue. Therefore, additional design solutions were needed, specifically drainage mats and a gravity-based drainage system. Drainage mats guide water to prevent it from accumulating, while the drainage system refers to the infrastructure that effectively manages rainwater and groundwater. Through this, water accumulation is prevented and flooding or water damage is minimized. The installation method for drainage mats involves placing them beneath the platform to guide water away from collecting in specific areas. The water guided by the mats flows into storm drain pipes and some pumps installed beneath the platform. The storm drain pipes direct the water into the sewage system, while the pump system discharges the water externally. It is designed so that the water naturally flows from higher to lower elevations. It requires no energy cost, making it an economically efficient drainage method. With all of this in place, the perfectly comfortable indoor environment and housing yards could come true. However, all of this would be meaningless without a solid foundation. We will now take a look at micropiling, the foundation system that made all of this possible at Hudson Yards. Micropiling is a structural element used to reinforce a building's foundation, creating using a small diameter steel casings or thread bars. Steel casing is an essential component in deep foundation construction, providing structural support, vertical control, and groundwater protection. It enhances the stability and load-bearing capacity of large-scale projects. Threaded bars are used in piled foundation construction, such as bridge piles, high-rise building piles, and dock piles. Since the deck spans over numerous rail lines, it required highly precise and delicate construction. Micropiling made this possible by supporting existing structures, even in limited spaces, while minimizing vibration to the existing foundation. Micropiling is similar to the roots of a tree. By installing numerous micropiles, it not only mechanically improves geotechnical conditions, but also significantly increases load capacity, effectively forming a unified structure system. The micropiling was fit to construct the foundation of the Hudson Yards project. Now, let's take a look into that remarkable process. First, 300 caissons, essentially large column-shaped pipes, are drilled into the bedrock beneath the tracks and filled with concrete. Since trains continue to pass through the yard, workers lower the caisson section by section, while avoiding moving trains, drilling as deep as 80 feet into the bedrock beneath the west side. Unfortunately, the rail yard is a narrow corridor where trains form tightly packed passages, leaving no room for massive caissons. And a series of trusses that span across the rail yard was the solution. The suspended portion of the platform structure connecting 10 Hudson yards and 30 Hudson yards is supported by these trusses. The columns and other supporting structures for 30 Hudson yards are positioned between the rail lines below. Additionally, the truss supporting the southern face of the tower spans across the tracks by as much as 115 feet. Due to the position of the tracks and tunnels, there are limitations on where caissons could be placed, allowing us to use only 38% of the site to support the buildings. Each time a new obstacle was discovered, the structural design of the platform frame was modified to accommodate new caisson locations, avoiding conflicts with existing tracks and underground utilities. Moreover, constructing the platform without disrupting train operations made the process even more challenging. The computer models were used to coordinate drilling and truss placement around hourly train traffic, allowing work to be carried out whenever an opportunity arose. Over the 2.5 years it took to construct the platform, 4 track shutdowns were required. But thanks to all these efforts, the perfect foundation of Hudson Yards was brought to life. Building on that foundation, an exceptional HVAC system was also able to be implemented successfully. Next week, I will show you the foundation and construction methods of 15 Hudson Yards, which was built off the Hudson Yards deck.
Together we will go. Together we will go.